In this section, section 1.5, I want to discuss the notion of infinite limits. And what those are, it's when the answer for the limit can be infinity. In other words, you know the answer to the question, what is the limit as x approaches c of a particular function, and that is, what's the trend here? Where is the y value trending towards? And sometimes the y value doesn't trend towards a finite value like 5 or 6 or 10. Sometimes it trends all the way off the page to infinity. So I want to explore that notion in section 1.5, which is infinite limits. So let's get started. And the way to do that is to maybe begin by looking at a particular function. This one here. A pretty straightforward function, 3 divided by x minus 2. I'm using one of the examples at the beginning of this chapter because if you were to discover the limit the way that we did with a table, you might notice that at x equals 2, there's a discontinuity. There is an undefined location on my curve. So we might explore the question of what is the limit as x approaches 2 of f of x. Now, you can't use direct substitution here because if you do plug the 2 in, 2 minus 2, 3 divided by 0 is, well, infinity, but I'm not sure which, plus or minus, so we'll say just undefined. But if we look nearby, we could plug numbers in like very close, 2.001 or perhaps 2.01, and you find that we do get a response from the function. In fact, here I get a 300. And here, actually, I get 3,000. I'm getting a very large figure. And maybe we go back a little bit here to 2.1, and you realize what's happening. What's happening is that the y value is not really trending towards any particular finite value. That y value is trending right up to very, very large numbers. If we went to 2.0000001, you would see that the y value would get much, much larger. So it looks like the trend here is towards infinity. In fact, positive infinity. Now, on the flip side, if we look over here at numbers next to 2, very close on the left side, 1.999 and maybe 1.99 and even 1.9, we notice a different trend. In this case, if you evaluate the function at 1.9, you actually get minus 30. Here you get minus 300. And here you get minus 3,000. So the trend is very different in this direction. The trend is towards negative infinity in that direction. So what's the answer? Well, recognizing the fact that the limit and the function value don't necessarily match. In fact, the limit, usually the function value doesn't play a significant role. If the function is undefined, the limit can still exist, and we can find it. Sometimes the limit is equal to the function value, and that's a good case where the function is continuous, and the function value at x equals c can reveal to us what the limit is. But the answer to this question is, in this case, unknown, because the question is, to what y value are we headed when x is approaching 2? From both sides. And from this side, we're heading to y value of, well, minus infinity is not a value, it's more of a place. And positive infinity is more of a place than a value. We're headed to 2 very different places. So, the limit as x approaches 2 of f of x does not exist because there's no agreement. So that's about all I can say about the limit, is that it does not exist. I can't say that the limit is infinite or that the limit is positive or negative infinity. Remember, limits don't exist when you do not get a match at x equals c. You approach from either side and you ask for a match. We couldn't be further off in this particular case. One side is trending to minus infinity, the other side trending to infinity. Well, what does that look like as a graph? here at x equals 2, the graph of this particular function looks something like this. There's actually a vertical asymptote right there at x equals 2, as you might suspect because of division by 0. And then there's another one over here. So now you can visually see that coming from the right side, we're trending towards positive infinity. Coming from the left side, we're trending towards negative infinity. And there's definitely no agreement here. However, there is something, not only do we just not get agreement, we're getting something very unusual happening, and that is the curve is shooting off the page to an infinite y value. Now, let's do another example. In this case, I'd like to do the curve 1 over x squared. Now, for the curve 1 over x squared, whether you do this with a table, or in this case, I'll just do it with a graph. I'll graph the curve. We get a curve that looks somewhat like this. So the question becomes, what is the limit as x approaches 0, right here at x equals 0 on my function? All right, well, let's observe. If we come at x equals 0 from the left side, it appears that the trend is positive infinity. If we come at x equals 0 from the right side here, or actually that's the left and right side here, we also are trending. We have some kind of agreement here. So when we have agreement, I guess we can call it out and say, look, we came from both sides and we're all in agreement that we're headed somewhere. So I would answer this question by saying that not just does not exist, but we're heading somewhere that's known. It's positive infinity. We can't ever reach it, but at least we know where we're headed in this particular example, and we're in agreement. Now, just as functions would never be called infinity, we would never evaluate them to infinity, we say they're undefined. Limits, also, we don't leave this positive infinity here. We would say that the limit does not exist, and it's not because there's no agreement. It's because the limit did not evaluate to be a finite value. So for limits, we have two requirements. One requirement is that you meet. You come at it from both sides. We're in agreement from both sides. The second requirement is that that location, that y value that we're headed to, has to be a finite y equals L value that we can call out. Y equals 100, 1,000, even a billion, but not y equals infinity. So this is an infinite limit. In other words, at x equals 0, the curve goes to infinity. So from both sides. So I would say that the limit is equal to positive infinity, and then beneath that, I would back that up and say does not exist. Okay? For the reason that the limit itself did not evaluate to be a finite value. Let's talk about vertical asymptotes. Now, vertical asymptotes are the very items that we need to guide a curve to infinity. So how do we get vertical asymptotes? Well, one way to get a vertical asymptote is division by 0. So in this example, you could say x minus 3 equals 0 will cause a vertical asymptote at x equals 3. But you have to be careful. It is not true that you can simply set the denominator equal to 0 to discover your vertical asymptotes. Here's a good example. Okay, we certainly know we can't cancel anything because pluses or minuses prevent you from canceling. However, I could do this and say that the vertical asymptote is located where the denominator equals 0, because we're dividing by 0. Vertical asymptote located at x equals 1. But I'm afraid that's wrong. So what's the difference? Well, the difference is if you look more closely here, you'll discover that if you factor this, there's a couple of common factors in here. Now you have to be careful. We're so used to just canceling things out, and you can't just cancel this out in this particular case. There's no question that there's something going on at x equals 1 here. So if you were to cancel this out, look what happens. H of x would become just x plus 1, and 1 plus 1 is 2. But wait, the way this function's written, x equals 1 is a problem area because 1 minus 1 is 0. 1 minus 1 is 0. It's 0 divided by 0. There it is again. It's the indeterminate form. So there is a problem at x equals 1. There's no question. But it is not an asymptote. So if you were to divide out a common factor, you could express the new function as x plus 1, but the new function doesn't work at x equals 1. So what is going on at x equals 1? That's the real question here. So be careful to jump to conclusions to believe that that is a horizontal asymptote. In fact, it is not. So let me draw the line x equals 1 for you. I'm sorry, x plus 1, y equals x plus 1. So y equals x plus 1 has a y-intercept of 1. So there's my y-intercept of 1. It has a rise over run of 1, so I'll run over 1 and rise by 1, and then I can connect the dots and I can make my line. So this is h of x right here. So believe it or not, this original function that looked like some kind of quadratic or rational function is really, when you divide it out, is just a line. But the way the original function was written, there is a problem at x equals 1. 1 minus 1 is 0. 1 minus 1 is 0 divided by 0. So there's a problem here, right here at x equals 1. What is that problem? It is not a vertical asymptote. It is just a simple undefined spot. So whenever h of x computes out to be the indeterminate form, and here are some examples of the indeterminate form, you now know what it looks like on a graph. The indeterminate form resolved on a graph usually looks like a little tiny undefined spot. It is not a vertical asymptote, and it won't cause your function to trend off to infinity. So I could actually answer this one graphically, and I could say the limit as x approaches 1, well, let's approach from the left side, and we're heading to 2. Let's approach from the right side, and we're heading to 2. The limit is equal to 2. And that's even though the function itself doesn't work there. The function value is indeterminate. It's 0 over 0. So don't set the denominator to 0 to find vertical asymptotes until you've divided out common factors. Okay. Let's look at another example where we are seeking vertical asymptotes. Let's take a look at this one. X squared minus 2x minus 3. And let's divide that by x squared minus 9. Now again, if you go too fast and you're looking for vertical asymptotes, you might decide to just set x squared minus 9 equal to 0, x squared being 9, and then the square root plus or minus 3. These are not both vertical asymptotes. So let's do a little factoring over here. F of x. Factoring it, you get x minus 3, x plus 1. Down below, you get x minus 3, x plus 3. And our new function, when you cancel out a factor like that, you got to realize that even though you canceled it out, the originally written function here has got a problem with x equals 3, because 3 minus 3 is 0, and 3 minus 3 is 0. So at x equals 3, the function originally is undefined. Somehow we need to reiterate that. So the way to reiterate that is, even though we've canceled it out, even though we've created a new function that behaves at x equals 3, we have to indicate that there's still a problem at x equals 3. And what is that problem? 3. 0 over 0 is a tiny undefined spot. That's what we should see at x equals 3. So what is the only vertical asymptote? Well, now you may set the denominator equal to 0 to discover it. And that's the site of a vertical asymptote. Well, if I were to graph this, let's see what this might look like. Here at -1, -2, -3, we definitely have a vertical asymptote, but the problem ends up being I'm not sure which way to go with this. Do we follow that vertical asymptote up to infinity or negative infinity? So what I'm going to do, I'm going to get a little help from my graphing calculator to fill out this table. Now, we already know to stay away from x equals 3. We already know that's a problem. So what I'm going to do is I'm going to put this into my graphing calculator and make a little table here in the neighborhood of x equals 3. Let's do that. So let's take a look on the graph of where we would like some information. I'm sorry, -3. I apologize. +3. No, hang on. I'm confusing myself. Let's review, guys. At x equals 3, there is a little undefined spot. Okay, remember, that came from here, 0 over 0. That left me with x plus 3 equals 0. That is the site of a vertical asymptote. So we do have that correct. But I don't know what's going on over here. So let's go to -3, -4, -5, -2, and -1, and 0. So why don't we get some y values on our graph here? -5, -4, -3, oh, error, we expected that, -2, -1, and 0. So I've got some good y values there to plot. So let's take a look here. At -5, I should be at y value 2. Plot that. At -4, I'm at y value 3. Let's plot that. Error here for -3, division by 0. At -2, I'm getting -1. Let's see where -1 is. Oh, -1 is down here. So that's about right there. At 0, I'm sorry, -1. -1 is revealing a 0. And at 0, I'm getting a third. A third is about here. So if we take a look at this thing here and we graph it, I think we can see the trends. We just connect the dots and we ride along this asymptote. So let's see if that matches the picture that we got here. And I believe this levels off like that, and this levels off like that as well. So take a look at what the graphing calculator came up with. Pretty much the same thing. So how would you answer this question? The limit as x approaches -3 on my function. I'd have to say does not exist, for the simple reason that we're not in agreement from the left or right. So I can't say positive or negative infinity on this particular example. If they're headed to the same spot, they're both headed up to infinity, I really do want you to write positive infinity. I can see where it's going, and then underneath it say, but it does not exist, because just like we would say a function is undefined when it's infinity, we say a limit does not exist when it's infinity. This is different. This does not exist for the sole reason that we are not in agreement here. Now, I did forget to put one thing on here, and maybe you're thinking about it right now, because this function is supposed to misbehave at x equals 3, and it certainly does. There's a little open circle here. That is the site of the indeterminate form 0 over 0, which leaves this tiny little open spot, 0 divided by 0. Okay. So I'd like you to try some infinite limits of your own, and I'd like you to maybe graph some of these functions, take a look at the trends on the graph, take a look at some tables, and boy, if you come at it from one side and that's going all the way up to positive infinity, 1,000, 3,000, 5,000, 10,000, and on the other side it's going down to -10, -100, -1,000, -10,000. You know what it looks like, but you can also graph it. And again, you answer the question for limits. You say, where was I headed? You couldn't be in much more disagreement than this, so you just say D and E. If they're both headed to the same infinity, reveal that infinity, plus infinity, and then back it up with D and E. Or maybe it's going down and you would say minus infinity, and you can also back that up with D and E. So that is it for infinite limits, and I want you to take a look at some of the homework problems. It does help to graph some of these and also build tables to understand what kind of vertical asymptote is this. Is it one where the curve goes to the same location on either side, or maybe it's split? So that will help you answer the limit question. Thanks, and we'll tune into the next video. Next video is going to really bring all of what we've done with limits to the forefront here, because we're going to talk about the tangent line problem. This is our first real calculus topic.